That's not happening.
Hey Coleman, where are you?
I'm at my dad's office. I'm about to go to the airport.
Where are you going?
Boston.
Okay. Can you zoom in on me? Yeah, please. It's just me today. Oh God! All right. Okay. You get better. All right. Constant presence. Hello, everybody. Oh, wait. There we are. No. I got half of you. And nope. Okay. He's traumatized by Greek class, apparently.
We are.
Okay. They have Greek with Mr. Harpin right before in the same room. Anyway, so the first thing I wanted to talk about, hold on a second. Kira and Matt are both not here today. So on the presentations thing, I was trying to reschedule things to I thought it'd be really, really cool for this friend of mine to give his talk from CERN, and that kind of pushed things around a little bit. I'm not looking to make people's lives a living hell or anything like that. I really think, this first checkpoint, honestly, all you need to do is talk to your group mates, poke around on the internet for 15 minutes, 20 minutes, see if you actually are interested in the topic, agree on one, go into Google Drive, create a presentation, give it some title, share it with each other and me. You're at checkpoint 1. Like that's 20 minutes, 25 minutes of time. Checkpoint 2, the skeleton or what did I call it? The storyboard. It might sound a little intimidating because to a degree, once you've got that, the rest of the presentation kind of puts together very, very quickly. But I think you'll find that it can happen pretty easily for you. So like, for example, I'm gonna take Henry. You're doing flash memory, right?
Yeah.
Okay, how much do you know about flash memory?
Very little.
Okay, right now, you can even take notes if you want. You and me, let's talk about this. See if we can come up with some titles for some slides. What do you think slide 1 is?
How computers used to use physical hard drives, I guess.
Oh, that's cool. I'd say that's slide 2. I say slide 1, title.
Well, okay.
But that counts, right? You get like title slide. You might need like a picture of flash sticks or something on there. So you just go in and you type in like title slide, picture of flash drives, picture of tablet device with flash hard drive in it. And then your second one, you already came up with, you said older storage devices. So older hard drive storage device, and some talk about that. All right, what do you think next?
start getting into the actual, like, how they work, I guess.
Okay, so you're gonna have a slide on how Flash happens. Okay, I think there could be something that could be a couple of slides. It could be like 1, 2, or 3 slides. Who knows? There might be a couple things you could do before that. That might be like, you know, how the people in this room have seen Flash. Talk about the things that were on that first slide and like remind people what things Flash memory is in. Right? Then you start talking about how Flash works. Maybe that's 2 or 3 slides. What do you think comes next after that?
Maybe where the technology is going in the future.
That could be a couple of slides, and you know, maybe there's some kind of conclusion that brings it all together or summarizes. And if you make a slide with each of those titles, you can, without doing much research at all, make a couple of bullet points on that slide to say, you know what, I'm going to look for this and this and this. Maybe you've gone online and, you know, just even done a Google image search and found a few pictures that you can toss in there that might help you have a framework for you to build the actual content onto your final presentation a lot easier when it actually comes time for you to have enough time to actually do the final work. So that could be it, guys, right? You might, in that process, figure out that, oh, there really should be a slide on this, or I really don't need this one. But that second checkpoint is massively important for your success, but I don't think you need to fret about it taking a huge amount of time. And I'm bringing this up because, like, Kira's on some college visits. I bet some of you might have some accepted students weekends or something like that that are going on. That's the plan I want to make. I don't want you to be intimidated by the first 2 checkpoints. I think you can do it easily, and that they'll help you finish quickly when you get there. If for some reason I'm crushing you because of other commitments that you have that I didn't know about, just get a hold of me, and we'll get back and we can try to adjust things. We are crunched a little bit because this is all over May 8th, and I am trying to stay away from interfering too much with AP weeks. But so just be communicative to me if you think that a deadline is going to give you too much of a hard time. But try to stick to those first 2 because they're going to help you, and I really don't think they're going to be as hard as some people might think they would be. All right, yeah, Kaylee.
Did you get my email that I can't present on the 21st or the 24th? Okay.
Yeah, and if you have dates that are on that list that you know you can't present on, let me know and we can figure things out. And if it turns out that I have to bounce my friend at CERN just for the sake of your sanity, and like, we can do that. I just thought it'd be neat. He's only there for a week, so he could give us the talk some other time. But I thought it'd be really cool for him to be sitting in the Large Hadron Collider talking to you with, like, people behind him working on the Large Hadron Collider. Yeah, Henry.
I think Friday the 24th, I have the rescheduled Calculus Bowl, so I probably can't do that.
With Coleman?
I think Coleman is dropped out. I'm not sure.
The Calculus Bowl? Okay. Well, just email me your conflicts, and I'll try.
So I'm going to. I'm going somewhere else, but I'm still going to miss that class period.
Okay. Just email me your conflicts so that I can try to plan things around them. All right. Totally worst case scenario, I suppose it's possible that we could work out a way to, it would be non-ideal, but to, like, you know, if let's say Henry had a bunch of conflicts and we couldn't find a way to fit his presentation in, we still really wanted to talk to Jared out at CERN. Maybe he and I could go on Blue Jeans, and if I'd email around and maybe, you know, if a few people are free, they could join in just to increase the audience size, and we could do like a miniature meeting to just get it done in that way. We can be flexible about it, okay? Wow, we have Coleman twice. So quantum mechanical. All right. Any more questions there? Yeah, he's back again. No? Okay. So I wanted to talk to you a little bit about magnetism, just to give you something to stand on for me to be able to give you my defense. That is another thing that I can cut if we need to. I'm not married to doing it, although that wouldn't put anything off necessarily. So, but magnetism is very cool, and it was my passion. So we'll talk a little bit about magnetism. What was your first experience with magnetism in your life? What was the first thing that you saw magnetically?
Two magnets sticking to each other.
Something is super loud.
I think it's Coleman.
Kaylee's comment was,
Coleman, can you mute?
Someone being murdered.
Yeah.
Why are there two Colemans?
There's never enough Colemans.
One of them put it for King.
There's two different angles of your face.
There's two different images, like there's two cameras.
On two devices.
You're in on two devices. Oh, okay. All right. Okay. So yeah, what was your first experience with magnetism? Yeah, Jasmine.
My dad basically, we were doing something in the garage with very strong magnets. My first experience was my finger getting pinched between two really, really strong magnets, and I couldn't pull them apart, and it hurt really bad.
Oh my God. Was like the flesh pulped, or did it break any bones?
It didn't break any bones, but it just pinched my finger super bad, and it kind of cut it a little bit. It just wasn't good.
Coleman keeps changing. I'm sorry. So was that your first experience, or was that like the first super memorable experience?
It probably was the first super memorable one, because I can't remember any other first ones, but...
All right, what about the rest of you?
Refrigerator magnets.
We'll go Kaylee. We'll looked like Eni had something too, but go ahead, Kaylee.
Oh, yeah, my father also out in the garage, always working on things. Our dads are the same. So he had, the little... I don't know, like a little metal dish that is magnetic, so you stick the pieces in it when you're taking something apart. You don't want to lose part of your car or something. And so I'd be trying to, when I was really little, I'd be running around the garage and probably taking it in the house too, just trying to get stuff to stick to it.
Awesome. Will, what were you gonna say?
My mom had one of those code magnets that said a company on it, and it just blew my mind because it stuck to the code without leaving a mark. And it was just
all right.
Played with that for a while.
Yep. I'm noticing a trend in all the things that you're saying, though, and it's true for everybody. Oftentimes, what people will say is their first experience was something like, you managed to color in between the lines, and your mom or dad or something like that stuck it to the refrigerator with a magnet. In common with all of these stories, your first experience with magnetism is an experience with permanent magnetism, magnetism of a material. And when you were a kid and you saw it happen, as we just kind of heard Will say, and maybe less so for Jasmine, it was magic. I mean, it was absolutely magic. For Jasmine, it was horrific pain, but it was magical. No other physical effect looks as magical in front of you. Why? What's so weird about it in comparison to other things? Yeah, go ahead, Will.
Because it kind of defies gravity without anything concretely changing. Except proximity.
Yeah, it defies gravity. Absolutely. Eni.
Things normally don't stick to each other.
Things normally don't stick to each other.
When they do, it's kind of cool because magnetism is a stronger force than gravity.
Yeah. What about electrostatic forces? I mean, you got to see those. You'd rub the balloon on your head and stick it to the wall, or maybe you played with snap circuits and powered a little motor, made a thing. I don't know. What about electricity? Was that as magic to you?
Just wanted to follow up.
Coleman, I think your second device is still transmitting sound.
Well, and my record says we sit. So
there we go. Why did it feel more magical, or did it feel more magical to you? Go ahead, Will.
It didn't wear off. It just stayed there forever.
Yeah, that's exactly where I am on it. It's like, gravity is the only thing in your life that you see constantly present, like this weird force that just shows up out of nowhere. But you're so used to it, you don't think of gravity as being out of the ordinary. Although really, in a lot of the same ways, it seems magical. Like I just place this object here, and a force suddenly appears without anything touching it that I can see. Magnetism's the same way, but it's like compact. You can carry it in your pocket. And the only other things that do that need batteries in them, right? Like you need a source of power. You need to expend energy, and somehow permanent magnets just seem to be able to do their thing all the time. And hold on, I want to get something out of my room that I think you'll enjoy. Mr. Gleason, can you dance a little bit for them while I'm not, or like just speak Spanish to them about something? Hold on.
You guys don't really expect dancing, do you?
I do. Where's the dancing?
My brother-in-law taught my son how to do this. He said, "Let's make a finger dance."
Wow.
That's all I got. I can't do spontaneous dancing. Sorry. In the meantime, Coleman, how many devices are you on? How many devices are you on, and why, Coleman? Because it looks like your sound is on one device and your video is on another device. And if you're talking right now, we can't hear you because. Oh, okay.
Can you hear me now?
Yeah. So what is your sound? So the one that's not pointed at you is your sound. The one that is pointing at you is just your video, right?
Yes. I was using the one that was pointing at me for both, and then it stopped. Oh wow, that's really weird.
So you have your phone for the sound, is that right?
No, I have a tablet because I'm gonna have to leave halfway through. And
okay. So you have a tablet for sound. Well, your tablet's video is working. If your tablet is doing the sound, your tablet can just do your video too. If you want to just worry about one thing, you can do that. If that's easier for you.
Probably.
Did you just pour all over the table?
The burned ashes of problem students.
Oh, those. Okay.
No. I think this will work out okay.
Can you zoom closer or not?
I don't know, can you?
Probably.
I mean, like, there's just no doubt that this is magic. There's no way around it. Like, come on! Nothing is cooler than magnetism. It's just so awesome to look at. And you can see fields. And you learn about electric field. And you're like, yeah, okay, electric field. Can I see that? And you're like, no. But magnetic fields, you can see their shape. And you can do crazy things with them.
Change this to a big
What?
active speaker out for everybody.
Oh.
Now you'll be all.
I mean, it's cool. Magnetism is neat. And then you can do other things with magnetism that are sort of cool. Zoom back out for me. Yeah.
I got you.
Have you seen this demo with the copper tube? Some yes, some no. Right? Well, it's always fun to see anyway. I can stick, especially at an angle, I can put a pen in here and drop it through the copper tube, and the pen falls out. It's so exciting. But of course, I drop a strong magnet through. Right. So, it actually, oh man, oh wow, you can't see that. Can you see that, Josh?
Whoa.
Iron filings got on the outside, so it's actually sticking through to the iron filings on that side. That was really cool. Sorry you can't see it, but yeah. long time for it to fall through. Because it induces currents in the copper, right? And this is sort of like the baby version of the Meissner effect, that it resists change in the magnetic flux. So we've always loved magnetism. It's always fascinated us with its behavior. But it turns out that the magnetism generated by electric currents that you learned about later in life was much, much easier to explain with laws of physics. And that magnetism in materials was not well understood and not at all explainable without quantum mechanics and solid state theory in general.
I'm going to go back to constant presence.
Oh, well, actually, I'm going to go back to share screen.
Either way. It's still constant presence.
Okay. So there are several kinds of magnetism, of which you may have heard of more than one, but I'll talk about them now. You can have a chunk of material where there are magnetic moments within the material, but they don't get organized. This thing is not going to stick to the refrigerator. But if you apply a magnetic field through it, a magnetic field B, these moments align themselves with the magnetic field and suddenly start behaving like a magnet. As soon as you take that magnetic field away, however, the magnetic order is lost, and they fall apart yet again very quickly into a disordered state. Does anybody know what this kind of magnetism is called?
I only have paramagnetism.
Paramagnetism. Yeah, this is paramagnetic. There's also diamagnetism. Those are materials such that as you apply a magnetic field, the moments orient themselves opposite the field to reduce it, which is again like a similar kind of effect to Lenz's law and to the Meissner effect. But then, there are these others. Now, you've probably heard of ferromagnetic, and those are the things that have always fascinated us. Those are the objects that are ordered on their own, which is a strange thing to think about. How did they do that? How do they organize one another? How do they decide what direction to be organized in? The other two are less commonly taught, but you may have heard of them. If you've heard of paramagnetic, you might have heard of these. Antiferromagnetic, where the moments are well ordered within the material, but they're ordered in anti-parallel arrangements so that when you play with it, you think that it has no magnetism at all. It actually has strong magnetic moments, and they are well ordered just like a ferromagnet, but their anti-parallel arrangement makes it seem as if they have no magnetic order. A ferrimagnet is just like an antiferromagnet, but if you look, the opposing moments are weaker than these moments, so that the net effect is that they behave a lot like a ferromagnet. What are the differences between these things? How do they get ordered? And again, how do they decide what order to be in? I don't want to show you that yet. What do we know generates magnetic field that we learn about in intro physics courses?
Currents.
Current. What's up, Jeff?
Back to constant presence, the way you're sharing. So if you unshare,
oh,
and then constant, they'll see each other.
Okay, sorry. Hold on a second, guys. I have something. So stop share, constant presence, apply. There we go. Share speed. There we go. Okay, so I make a current, and what do the magnetic fields do around a straight line current? They don't dive around. They go around it. They go around it in circles. I'm just doing this in AB physics right now. If I use that fact and I loop a current into a circle, as I follow around with that current, the magnetic field it produces, while it might swirl around like right here, it would swirl around like this way. On the other side, it swirls around this way, and what you notice is that the magnetic field from each of these little points simply points down into that circle, which we often denote with X's pointing into that circle. Although if we were to look at this on edge, like that. Can you kind of picture what I'm talking about, like the loop of current on its edge? Magnetic field, of course, looks like this, which is known as a dipole field. Maybe you may or may not have heard of. If I stack those coils one on top of another, I don't want you to see that yet. I don't want to use that yet. Like so, and I send a current through, the magnetic field gets kind of straightened out in the middle and doesn't really arc as much. The thing that's interesting about that is if we take the classic permanent magnet that was not all that well understood and look at the magnetic field that it generates, it looks very much the same as the magnetic field generated by this solenoid, this collection of coils. So what is the suggestion then? This is predicted by classical physics. This is the thing that we've known about for thousands of years with no explanation for. What is the possible answer that one could anticipate that this thing on the left means about how this thing on the right works? Yeah, Jasmine?
That it makes a current, so it will act in the same way.
And specifically, what kind of a current?
In one direction.
Well, in one direction suggests to me something like this. Right? What is the current doing in this example here? Going around in circles.
Yeah.
So if we wanted to produce a magnetic field, we could hook a battery up to a coil of wire. We could get the current to circulate around in these circles, and it would make this magnetic field. And so the question comes up, where is the battery? And this is what Will was talking about, that magnetism is magical because where is the source of power to constantly supply current to constantly generate magnetic field? This magnet has been at my school for 37 years. The batteries have not run out on it. And that is magic to us. So what are the currents?
Electrons.
What do electrons do inside a piece of material?
Orbit.
They either orbit their nucleus.
They orbit. That's one thing that they do. Let me just erase this. Got a bunch of images I want to show you later, and they're kind of taking up a lot of space. So if I had like an atom here, there are electrons that are orbiting around them. Wait, hold on. What class are we in? No, they don't. They do not orbit in circles around the nucleus. Thank you very much. That is not what happens. But let's go with it for a minute. That could produce the dipole field. Now, that is certainly not the case for how electrons behave around a nucleus. But it still might be true if you look at the periodic table that there could be what's called net orbital angular momentum. That's what we're really talking about here. If those electrons have angular momentum, if there's some kind of rotation, then they should, because they're made of charge, make a magnetic field. The trouble is, and we won't go through this in detail, there are very few atoms on the periodic table that have a net orbital angular momentum on their own. The ones that exist are all lanthanides and are horribly deadly radioactive death. I'm pretty sure that the magnet that crushed Jasmine's finger or stuck to the back of Will's car was not highly radioactive. I'm just going to guess off the top of my head. So it was not angular momentum. And those magnets are quite weak, by the way. So if it's not orbiting, what's left for the electrons to do to make a magnetic moment?
Move forward. Free electrons.
They could, and that's what's happening when you drive a current through a wire, and they make magnetic fields. But this thing, again, making a dipole field, as that shape is before, so in order to make this field shape, they have to be circulating. So what can they do besides orbit?
Spinning.
Spinning. So here's how the explanation starts to go initially. That is very wrong, but is nonetheless the way people talk about it. We say, like, all right, let's say we had an atomic lattice of iron. Okay? If we look at the electron valence structure of iron, it ends in 3d6 or S2. That may be the set of letters and numbers in that pattern that you were least excited for me to ever write. But that's how the valence ends for iron. Now, you've taken chemistry. Think, how do, like, this state is completely filled up. That has no net spin. But how do we fill up and figure out how the electrons are configured in this D state? What do I do? I'll give you a hint. We draw 5 lines. Probably your chemistry teacher did
You
that.
draw them up, and then you have to draw them all up, and then you go back, and then you draw them down.
Yeah, you fill up first. We're like 1, 2, 3, 4, 5. And we filled those quantum states. That's what we're actually doing. And then the next electron goes in the opposite spin, 6. Now look, this is saying that an iron atom has a net spin of 4 electron spins up. I'll just draw one arrow to represent the fact that it has a net spin, according to Hund's rules from chemistry class. And then what they then say is, like, and then what happens is each of these atoms has a magnetic moment, like they're their own little bar magnets, and they all kind of like talk to each other, like, Jim, this way, right? And then that one talks to that one, and that one talks to that one, and they all get organized, and every piece of iron is a magnet. Not at all. That's not true. Not every piece of iron is a magnet, first of all. And second of all, there's something, I mean, in all honesty, once you learn the real thing and you work in the solid state physics for a while, you still use this model to think about it because it's simple and you can conceptualize it easily. But there's something very disturbing about all of this. The way that a chunk of iron could be a permanent magnet is that very thing that we just said, that these magnetic moments could talk to one another so that they could team up and point the same way. With our paramagnetic material, they have magnetic moments, but they don't talk to each other and get organized. But what is super, super, super wrong with this model? What is iron? What kind of a thing is iron?
A metal.
A metal. What electrons are these? Where do those? What are those?
They're the valence, the 3 ones.
They're the valence electrons in a metal. Where are the valence electrons in a metal?
In the electron sea.
In the conduction band in the electron sea. So then let me say the question one more time to you that have taken a little bit of quantum mechanics. Where are these electrons in our block of iron?
Somewhere.
Everywhere.
Everywhere.
If they exist at all locations in the solid simultaneously, how can they be organized atom to atom to an alignment? How can electrons in the electron sea have an organization that is affixed to the ion cores to which they aren't attached? It doesn't make any sense. It's like saying that dust particles flying outside our solar system are organized according to the planets. What are you even talking about? So what's going on? The other thing that's upsetting is that on the periodic table, the only chunks of pure elemental material that exhibit magnetic properties at all in this way are iron, cobalt, and nickel. And you'd think that anything that ends in 3d6 or d6, anything under iron on the periodic table should behave in exactly the same way as iron and be a magnet in exactly the same way. And they aren't. So there's clearly not enough information in just Hund's rules and the fact that there's a net spin on an atom. And I would love to say to you, what do you think the problem is? What do you think the answer is? But that is not a question you can easily answer at all. So here's the way it goes. Around each of these atoms in the valence band, if the atom were to be alone, the valence electrons would have a particular orbital structure. When you start to form the solid, depending on the crystal lattice spacing and the shape of this orbital, those orbitals become deformed as they interact with one another, changing the shape of the orbital to something else that it wouldn't have been. The structure of the electron C gets affected. It's not the simple square root thing I said it was. I was lying to you a little bit. But as those wave functions overlap with one another, they deform each other, and what happens is this right here. I think I can move this up. I think I have room. Yeah. Erase. What happens is that regular old density of states that look like this, if we unfold it and kind of turn it on its side, we could split it up into a density of states. It's the same kind of thing, but we have like spin up over here and spin down over here. And in a normal material, we have 50% of the spin up and 50% of the spin down. And even in a material that has a net magnetic moment, has a net spin, ends in 3d6, for the entire solid, this would be evenly spaced. When we apply a magnetic field to a regular old paramagnet, spin up and spin down are in a different energy state, and you shift this that half of the conduction band down and this half of the conduction band up. And so when you go to fill up the states, you get more spin down than spin up, which is depicted over here on this thing. What's interesting about a ferromagnet is that those overlap wave functions generate a built-in split in what's called the spin-dependent density of states. So that even without a magnetic field applied, they apply their own magnetic field effectively on their own density of states to shift it so that there are more of one spin than another. That's pretty complicated. But it has to be an explanation in terms of the behavior of the conduction band. It can't be ascribed to each atom individually. When I apply magnetic fields, what I'm doing is shifting the spin-dependent density of states. Now, where's that other image? Now, even when I do that, within a chunk of magnetic material, it can split into domains. Because we still haven't said, if they're going to get organized, how do they know which way to be organized? And if it's just a regular old chunk of iron, they kind of locally get organized in one kind of random direction, but a neighboring chunk of iron is organized the other way, and another one is the other way, and another one's the other way. And so just an average chunk of iron, it is a magnet. It obeys all these rules, but it still doesn't stick to your fridge. What you have to do is heat this thing up and melt these boundaries. You apply a strong magnetic field to it while it's kind of melted, and then you cool it down. And as you cool it down, these domains line up with one another, and it cools down with all those domains pointing the same way. If you've ever used a really old hammer or a really old screwdriver, you may have noticed that as you use it for a while, the end of the hammer or whatever gets hot. As it gets hot, it loosens up these little magnetic moments, and the Earth's magnetic field, this gentle little magnetic field, serves to kind of gently organize these domains together. And as you keep heating and cooling it, and heating and cooling it, and heating and cooling it in the presence of Earth's field, a 80-year-old hammer will eventually have it such that the nails stick to it because you have aligned the domains over time, which is kind of neat. Now, what would be really cool is if you were able to actually see those domains. And that's what these are pictures of. We can take pictures of magnetic domains. It turns out that the way that polarized light interacts with different magnetic moments. The way something is magnetized and the way light is wiggling changes how well they interact. And so you shoot polarized light at a magnetic material, and it photoemits electrons using the photoelectric effect. And if the magnetism is well aligned with the polarization, you get lots of electrons coming off, and you see that the magnetism is pointing in the direction of the polarization. This chunk of material had electrons that were pointing mostly in the other direction. This is called PEM, photoemission electron microscopy, and it's really, 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 really cool. Down here is a picture of a PEM. I found another one. Where did I put that other picture? Is it over here? Nope, not there. Maybe it's at 4. Oh, where's my super cool one? Well, I'll go like this. Yeah, there you go. That is a PEM, which honestly just looks like an anime weapon to all of you, I would assume. The reason I'm showing this to you is because, I mean, come on, you want to play with one now, right? You don't know what it is, but you know you want one. They're like $150,000. The one that I used was ridiculously expensive. You need a synchrotron to operate it. Let's see if I have a picture of their operating characteristics. Yeah, they work sort of this way. You send in polarized X-rays, they photoemit electrons out, and then you have to make all that. The rest of the device are these chunks of metal that make electric fields in kind of curved shapes that bend the beam of electrons just like a lens in a camera to focus an image. This is that same microscope I told you about a while ago that's also chemically specific. So these pictures are not only pictures of domains, but they're, see if it says here. Yeah, this is a picture of iron, and the kind of weird staticky stuff on the outside is other materials that it's not interacting well with. And then additionally, you can get magnetically specific image. So you can say, I would like to see things that are made of iron whose magnetic moment are pointing to the right. And it will give you pictures of only that, which was, wow, Coleman's somewhere very nice. Which is, completely blew my mind. And I was very excited to play with one. How am I doing on time? So, after all of this, what do I want you to know about? In an average chunk of ferromagnetic material, it is helpful to think about it like what happens is that the magnetic moments on each atom that come from Hund's rules generate a net spin, and that if they are properly organized, they talk to one another and orient themselves in the same way to become a ferromagnet. That is a completely unsatisfactory explanation. I would be super, super excited if you were to kind of have this awareness of ferromagnetism, but to know the little fact that also, no, electrons see. Those electrons aren't local. They can't organize that way. That doesn't make any sense, quantum mechanically speaking. And then I would love for you to be aware that what's really happening is in the conduction band, there's a density of states. Typically, it's evenly filled, spin up and spin down. But in the presence of a magnetic field, it is shifted. One becomes easier to be in than another. And that should make some sense, right? If I have a strong magnet, where's my little tiny magnet? I'm stuck to this thing. Yeah. If I have a strong magnet, let me go off of sharing. If I have a strong magnet and I put it near another magnet, if you watch my hands, I can't, it wants to point in one particular direction. Turning it the other way is hard. It doesn't like it. And then when I let go, it orients itself into a more comfortable position. What's happening is the Pauli exclusion principle is winning. It's more comfortable to be in this state. And so there are more states this way, but eventually those fill up. And there are the next best that the electron can do is to be in the uncomfortable, more difficult orientation. So that I care that you know, so that the thing I need you to be aware of when I continue to talk about other things is that what characterizes a magnetic material in the end is an abundance of one spin of electron versus another. I'll also drop this little bomb. Without this model, consider, if you will, how on earth would antiferromagnetism work? What is going on with ferromagnetism? How does this operate? How are those spins localized to be different in size and in different orientations? There's clearly a lot more to know here. And the other really scary thing is that all of those superconducting ceramics that we were telling you about that were high temperature superconductors, all of them are antiferromagnetic. Which, if you remember how BCS theory works, how the Cooper pairing theory works to make superconductivity operate, you can certainly see that there's something enticing about that. And when I was in grad school, that was a really big question that has started to be answered like this year. So when we get back together next time, I hope I can stand on the very basic level, where did I do with my little drawing here, of understanding of a spin imbalance being present in the valence band, so that I can explain to you how it is that my magneto-optic Kerr effect magnetometer worked, which would be kind of fun to me, hopefully. Do you have any questions for me about magnets? They can be really general, or they can be about some of the stuff I was talking about. I'll go off of my device share. Okay. I guess we're a little bit early, but that's fine with me. I will see you on Tuesday. Just make sure you're getting a hold of me if deadlines are creating huge problems. I think we can stick to them. Please try to hit those first two without much trouble, I think. But then from there forward, please feel free to ask me to be flexible, as we'll help you, or to ask me for help finding resources or material. All right? Any questions about projects for me that remain hovering? All right, and then one last thing. Give me some indication. Is the possibility of talking to a scientist while he's at the Large Hadron Collider actually of interest to you?
Yeah.
Yes. Better than him just like coming and hanging out with us on camera here.
A little better.
Yeah.
A little bit. Okay. I've also asked him to see if he can get other scientists in the room to come and say hi and tell you what they do. He's not sure how many people will be there at the time of day he would be talking to us, but we'll see. All right. I'll see you guys later. Drive safe, Coleman.
Bye.